Okay, this is video 2 of lesson 4.3, solving polynomial inequalities. And in this example, we are looking for the solution to when this polynomial, this degree 3 polynomial, is greater than or equal to this quadratic polynomial. And this appears different than the example that we've already done. However, it is very, very similar. And the reason it's similar is because you can rearrange this inequality to look like the question you just did. And how do you do that? Simply by moving all the terms to one side and having the inequality read as greater than or equal to 0. And then you are basically just looking for a single polynomial and where it's greater than or equal to 0, and it makes the question much easier. The alternative would be to graph both of these and look for where one function's above the other function, and that can get quite messy. So let's try this strategy of moving all the terms to one side to simplify it. So I'm going to start, x cubed is the only cubed term, so we have an x cubed. On the left side, we have negative 2x squared, and we're going to move the plus 2x squared to the left side, becomes negative 2x squared. We have plus 5x, we're going to move the 14x to make it negative 14x. We already have 20. We're going to move the negative 16. It becomes plus 16. And we're looking at when it's greater than or equal to 0 now. Add your like terms. You get x cubed minus 4x squared minus 9x plus 36. And now we're looking for where this degree 3 polynomial is greater than or equal to 0. The question is now much easier. How do we approach this? Well, we factor it. So let's try factoring. We're going to use the factor theorem and think of some factors of 36 that we can substitute in for x and see which give us a value of 0. Factors of 36 include 1, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Wow, there's a lot. I have superior factoring abilities, and I'm going to guess that 3 works. So I'm going to test that. I'm going to call this my function f, and I'm going to say function at 3, and I'm going to do some quick calculations and say, oh my gosh, it does equal 0. I am a genius. That sounds pretty pretentious. But anyways, it does work. So 3 is a factor, and now I'm going to do some synthetic division. 3 into our degree 3 polynomial. We've got 1, minus 4, minus 9, and 36 are my coefficients. I don't know why I wrote the plus there. Anyways, we'll bring down the 1. 3 times 1 is 3. Add down the column, we get negative 1. Multiply by 3, we get negative 3. Add down the column, we get negative 12. Multiply by 3, we get negative 36, a 0 remainder. So that means we have a partially factored x minus 3, because our root was 3, times x squared minus x minus 12, which, if we try to factor, we're looking for numbers that multiply to negative 12 and add to negative 1, and we've got negative 4 and positive 3. So there we have it factored. So what are our roots? Well, our roots are negative 3, 3, and 4. So from left to right on a number line, negative 3, 3, and 4. I'm going to write my factored polynomial up here again so we have it. X minus 3, x minus 4, x plus 3. So we've got our roots, or our zeros in this case, which represent our x-intercepts. Our factors are x minus 3, x minus 4, x plus 3. Order doesn't matter on the left, or sorry, down the left column. You can put any factor in any order, because when you multiply numbers, order doesn't matter. Order does matter on the top because you need intervals that make sense. So x equals 3. To the left of x equals 3, that would be x's that are less than negative 3. I don't know why I said x equals 3. X equals negative 3. So we need numbers that are less than negative 3, so x is less than negative 3. Then our next interval is between negative 3 and 3, so that would be x is greater than negative 3 and x is less than 3. Notice there's no equal signs in any of our intervals. The equal signs are accounted for by writing your roots on top. And then we have to consider them when we write our final answer. Since it says greater than or equal to, we need to add the equal to our intervals for our final answer only. If there was no equal sign in our original question, we would take the intervals as we wrote them in our table as part of our answer. Next interval between 3 and 4. So x is greater than 3, less than 4. And our last interval, x is greater than 4. All right, let's test some values. A number less than negative 3, let's say negative 5. Negative 5 minus 3 is negative 8. Negative 5 minus 4 is negative 9, so we get another negative. Negative 5 plus 3 is negative 2, so we get a negative. A negative times a negative makes a positive, times a negative makes a negative. Our function is negative. We're looking for intervals where the function's positive, so not this interval. Since we have order 1 on all of our x-intercepts, we can assume that we are crossing the x-axis in all of our x-intercepts. So we should expect positive, negative, positive here. But let's complete the chart to check and make sure. And it would be good practice to check and make sure and complete the chart as necessary, because if you miss that exponent 2 and you don't realize that it bounces off, your whole interval chart's out of whack and you get the completely wrong answer. So let's finish the chart to make sure. Number between negative 3 and 3, let's go with 0. 0 minus 3 is minus 3, so it's negative. 0 minus 4 is minus 4, so it's negative. 0 plus 3 is 3, so it's positive. Negative times a negative is positive, times a positive is positive. Between 3 and 4, ooh, that's narrow. Let's go 3.5. 3.5 minus 3 is a half, which is positive. 3.5 minus 4 is negative a half, which is negative. And 3.5 plus 3 is positive, so it's positive. Positive times a negative is negative. Negative times a positive is negative. We are negative in that, over that interval. Greater than 4, let's go with 5. 5 minus 4 is 2, which is positive. 5 minus 4 is 1, which is positive. 5 plus 3 is 8, which is positive. All positives multiply to a positive. So we have two intervals where the function is positive. We're looking for greater than or equal to 0. Therefore, f of x, we'll call our original function f of x, is greater than or equal to 0. That doesn't really answer our question. So that's actually bad. I shouldn't write that. Let's go with we should restate the original question, and that's not what the original question was. The original question was, where is our degree 3 polynomial bigger than our degree 2? So therefore, x cubed minus 2x squared plus 5x plus 20 is greater than or equal to 2x squared plus 14x minus 16 when x is greater than or equal to negative 3, less than or equal to 3. Notice we added the equal to parts to our intervals because it's equal to in our inequality. And when x is greater than or equal to 4. If you wanted to write this in interval notation, since it includes equal to, we use square brackets. Square bracket, negative 3 comma 3 square bracket. And greater than or equal to 4, we would say square bracket 4 comma, and then greater than all the way to infinity, so the end would be infinity. Infinity always ends with a round bracket because infinity is endless. And there we have our answer, written in interval notation. And I guess that's it. Thanks for watching, and I guess I won't see you in part 4, or 4.4, because that's an investigation. So that's it for the videos in Unit 4. I'll see you again in part 5, Unit 5.